Cornell University to talk about the shape of things to come.
All right, so pleasure to be here today and talk to you a little bit about directions that I think rapid manufacturing and additive manufacturing is heading. We heard a lot about what is being done today, all these fantastic opportunities that are opening, but often the questions that we tend to think about is how can we reproduce conventional manufacturing? How can we reproduce conventional parts using this technology? At what point does it break even with conventional manufacturing? But really, that's not the right frame of mind. The frame of mind that you should think about is how can we do new things? What kind of new opportunities are opened by this technology? And this is really what I'd like to talk about today. And I'll show you a couple of examples of what I think are new directions. So I'm at Cornell University. And we work at what we call the Creative Machines Lab that makes machines that create and machines that are creative, and we'll talk a little bit about how that plays out. So here are the conclusions, just as in case we don't get there in time. The key idea is that we're beginning to go we're really at the beginning of a story. And what you've seen up until now is the first episode of what I think are 3 episodes. We have unprecedented control over the shape and form of objects right now. Complexity is free. You can make complex shapes at a press of a button. That changes engineering in a way that few inventions ever have. But that's only the first episode. The second episode, which we're beginning to see now, is that we can combine materials and control the internal composition of structures in unprecedented ways. We can mix and match materials inside in graded and complex ways, not unlike biology. That has opened a new paradigm of engineering that we're just beginning to explore. So instead of thinking about how can you control the manufacturing process to make the material uniform, think about how can you control the manufacturing process to take advantage of the control, the precise control and the non-uniformity at every single location, so you can optimize materials in ways that you couldn't do using any manufacturing method. The final process, the final episode, which will unfold in the future, is going beyond just structures and material and passive materials to actually working with active materials, being able to print electronic circuits, being able to print transistors, conductive, semiconductive materials, printing all of these things combined to really go from passive parts to active integrated systems so that you can eventually literally download your iPod and have it working. All right, so this is where we're going, and I want you, it happens to me all the time, I'm thinking, where was I back in when Microsoft had 10 employees? What was I doing, right? When Google had 10 employees, what was I doing? When Facebook had 10 employees, what was I doing? Don't think back 20 years from now, what were you doing when this technology took off? It's taking off now, and it's going to change every field, and no field is going to be untouched. So think about how it can affect your field. So with that in mind, I'll tell you a little bit about my own story. I got into this whole area from the direction of robotics. We were working on evolutionary robotics, trying to evolve robots, to breed robots using evolutionary techniques, genetic algorithms, and so forth. And we try to breed robots that can crawl across the table using parts that combine and recombine in random ways and are selected for their ability to move. We did that in a gaming simulator back in the late 90s. We had to write our own gaming simulator. We had to do all the dynamics. And we got these interesting machines that came out of this process. But I had to, I was trying to get a faculty position out of my PhD, and I was thinking, what can I do to give this an edge? Go beyond just making this in the virtual world into the physical world. And that's when I was exposed to this fantastic technology of 3D printing. And we took a 3D printer back at the time in '99, and we printed those robots completely and had them crawl around the floor. So the printers allowed us to go from the virtual world into the physical world and demonstrate how this process of automation can be used physically. That was enough to get me a faculty position. and it appeared on the front page of New York Times. You can't do that anymore with robotics, but at that time, back in 2000, that was below the fold, though it didn't get quite to the top. But the question is, how can we take that step forward? So I was already I realized I'm not going to get tenure by making plastic robots. Okay, I'm going to make something that's a little bit more serious. So when you look at this, this is a close-up of one of these printed robots. Everything about it is evolved and printed, but it's only the structure that's printed, only the plastic part, only the white part. The wires, the batteries, everything else we had to manually put in according to the evolved blueprints. So our goal became, how can we make a new kind of printer that will print the entire robot? We literally want the robot to walk out of the printer, batteries included. All right, how can we do that? If we can do that, we can really change engineering and combine that with design automation, and all bets are off. So this is really what we want. And since then, we've been doing a lot of printing of robots. In fact, I dare say that there's probably no robotics lab on the planet that doesn't use 3D printers, because there's no better way to make things. This is recently a flapping, hovering 3-gram flapping ornithopter. It flaps its wings and hovers like a mosquito. It's 80% printed. We did that in the lab. There's no way we can do this with any conventional manufacturing method. So it really changes everything. So what kind of technologies, and we've heard quite a few of them, what kind of technologies will allow us to print combined integrated systems? It's definitely going to be the kind of technologies that bring the material deposited, like a continuous stream or inkjet, that allow us to work with multiple materials at the same time. And so we set out to make a printer that can work with multiple materials, active materials, in order to make some of these things. And cut a long story short, we started off by printing simple things like strain gauges with the wiring embedded, printing batteries. This is an example of a printed battery. The chemistry of a battery is easy to come across. What's difficult is printing all the materials in a way that allow them to be mutually compatible. So, for example, a battery has 5 materials, easy to print, except one of them. One of the structures of batteries is a separation layer, which is typically made out of paper. Now, ironically, we can print everything, but we can't print the paper. So we had to find a new way to print a separation layer without paper. And so that was a challenge, and we found that. And we can print a battery. It's about 50% of the capacity of a commercial battery, but it can be printed in any shape. And that means you can do engineering differently. You can embed batteries inside the structure in interesting ways. What about motors? We have to give up on this idea of electromagnetic motors and maybe think about actuation in a different way. This is an electroactive polymer made of 5 layers. You print them, you connect it to voltage, and it flexes. So this changes how we're going to think about robotics, and this is just an example of how this technology changes things. We're still on our way to try to print a robot that will walk out of the printer. The student that did this convinced me to let him try to make a robot that will swim out of the printer, which is a little bit easier, and we're still trying to do that. So whenever I talk about this, people say, okay, yes, they get excited in the beginning, and then they say, okay, what's the killer app? What's the big thing that's going to change? Okay, you have all these small things. So that's a really difficult question to ask with such a generic technology. Is it printing parts that we've seen a lot? Maybe that's the killer app. Maybe it's printing toys. A lot of people are actually printing these kind of figurines and pictures of their friends. Somebody told me it's the easiest way to make friends now is this way. Maybe it's going to be fashion. You'll be amazed to see how many people are doing fashion. People who don't care about manufacturing, engineering, or anything, but care about fashion suddenly are drawn to this. This is titanium. There's, of course, no other way you can make something like this. People design it, make it, and sell it. There's bikinis that are now printed. I didn't want to put the slides here to show that, but there are lots of them that they sell for $400 a piece. They're a bit too coarse for my taste, but there's a lot of these options. Printing cuneiforms. We did that. We scanned cuneiforms. We print them. They have the shape, the feel, the color, the weight, the texture of a real cuneiform. They're almost indistinguishable. Fantastic for historians, for archaeologists to look at these things. Maybe that's the killer app. I don't think so. Somebody talked about custom prosthetic devices. Definitely a big area. We've talked a lot about already about medical devices, and I took out a lot of slides because there was an excellent presentation, but definitely in this area, training, if you want to train surgeons on pathologies and you can't find the cadaver with the right pathology, you want your surgeons to train on models. Hearing aids, we've heard about that. Surgical planning, we heard a lot about that. We almost do this routinely now at Cornell with the med school, and especially we do this sometimes. We print these models before they go into surgery, and they train on these models before they actually do before they go into surgery. Especially in vet school, we routinely get these emergency calls. A dog has been run over. Here's the file. We print it, and they can cut down the surgery by half. I think the regulation in vet school is a lot less, thankfully, than it is with humans, and so they can experiment like this a lot. We heard a lot about implants, but one thing I wanted to add is printing directly with live cells. This is a bioprinting. There's a kind of a growing area. This is some things we've recently done, printing with cells directly. In this case, these are cells which we harvest from the meniscus of a knee, cartilage in the knee. We take those cells, we culture them, we put them in a hydrogel, and we extrude them in the shape from a CAT scan. And this thing, you incubate that. It's a meniscus ready to be implanted, and it's basically a original part. It's not a part from plastic that's going to wear out or from titanium. It's an original part, your own cells, and it's ready to be implanted. This is the easiest meniscus cartilage is the amorphous tissue, so it's challenging, more challenging to do that with bone, but bone is next, liver, and so forth. So this is printing with soft tissue, and there's really no reason to print this outside and implant it. One of the interesting things, and we've done a little bit with this, is to print it inside, in situ. So not printing outside, but printing inside. So these are examples of ways you can really take this technology and change the way things are done. It's not about replicating the way traditional implants are made, but better, but actually creating new procedures. Maybe the killer app is going to be models, making teaching models and so forth. We have a lot of these teaching models from 1880 at Cornell. We have them all online, but unlike any other museum, you don't just look at these models. You can also download and make yourself a copy of these mechanical instruments. And people are downloading them to teach mechanical engineering in other places. So that's a new kind of museum that you can't work with. But still, doesn't sound like the killer app. And so turns out that in the computer industry, back in the 70s, the big companies, IBM and Honeywell, were also struggling with the question, what is the killer app of computing? And there are a lot of similarities that people notice between 3D printing and computers, right? They're expensive, slow, and big back in the 70s. And today, they're all small, fast, and cheap. So what has changed? We're following the same trends. You know, we think about we try to think about what happened back in the mid-70s that the whole thing took off. And so what's the killer app? The Honeywell and IBM tried to figure out what's the killer app of computing, and they came out with this machine. It makes you cringe when you see what they wrote there. They thought it's going to be the computer. The computer is going to be in the kitchen. Right? That's what it's going to be. So this was a big flop, but it turned out the actual killer app came from the market itself. From what happened when the prices went down, when the first computer kits came out, people started building their own computer kits. The Altair 8800 came out in '75, and people started making lots of them. There were lots of them out, so people came out with their new ideas, wrote software. There was reason to write software because there were computers. There were reason to make computers because there was software. The whole thing took off, and the killer app was gaming. Gaming was the killer app. All the hackers built that up, and IBM and Honeywell could not anticipate that that's the thing. So what's the gaming app going to be for 3D printers? This is the Altair 8800, cost about $400 then, about $2,000 today. So we don't know what it is, but we know one thing for sure. We got to make these printers cheap and hackable and let them loose and see what people do with them. So we made the Fab at Home This is Fab at Home Model 1. Since then, this is the Model 2, this Model 3. It's completely open source hardware and software. People build these all over the world. There are others that came along, different varieties. You hear about them in the news now all the time. Brent just said there's more of these being built and sold than all the other commercial ones. They come as kits. You assemble them like IKEA. You put any material you want in them, from cheese to silicone, and print. And people are making all kinds of things with these printers all over the world and doing all kinds of experiments. If you want to try this technology with your own materials, with your own ideas, you don't have to settle for the commercial expensive machines where you void the warranty if you make any change. You can go with these hackable systems and do whatever you want. Here's the RepRap, which spun off MakerBot, which you might have heard of. If you haven't, you're going to hear about it. Just acquired for $10 million. These things are going wild. I just came back from Maker Faire this weekend in New York City. These things were littering the sidewalks, okay, these replicators. So we can print from anything from cheese to titanium, all right? So there's no material you can't print with. You can print in combinations of materials, and really the sky's the limit. Foam materials, ceramics, and so forth, and people are making everything from Lego to iPod covers to robots to bicycle gears and anything you want. So what's the killer app? So we let this thing loose, and a couple of interesting things happen. Now, it's all over the place. I just want to show you two examples of things that I, at least, did not anticipate that people will do with these things. The first one is cooking, okay? People like printing with chocolate, peanut butter, frosting, cake, and the cake pan, brie and pesto, you name it. So putting all these materials, and this is opening up to be this new area called digital cooking, where you have this CAD software, you say what you want, how you cookie, the graded crispiness of it, and all that, and you hit the print button, and it makes it for you. People are making all kinds of things. This is the French Culinary School printing scallops and celery and frying them with one of my students. And this is fried dough, printed in some crazy shape. And just a month ago, a cab driver stopped me in New York City, asked me, "Are you the guy that's printing fried dough?" And, you know, I hate that to be my legacy, but if that's what it takes to bring people to manufacturing, we'll do that. So we harness America's love for fried dough to bring them into engineering. I think that's going to be the key. All right, here's a cookie. Looks like a regular cookie. You cut it in two, there's text inside. Okay, new way to send passwords. There's lots of different ways, lots of new applications, and I think it's interesting. The second connected area, which we haven't mentioned, is education. So it turns out that kids who couldn't care less about science, technology, engineering, when you talk about printing cookies, they're suddenly interested. When you talk about printing Play-Doh, they're interested. And we have this Fab at School project, which puts these printers in elementary schools, and we're looking at how to change curriculum to allow kids to engage in manufacturing on the spot. I showed this printer to my son's second grade, and kids were suddenly, we printed shuttles out of Play-Doh, and suddenly they were calculating, one kid was calculating how many shuttles he can print with one block of Play-Doh. Another one was calculating how much profit he can make. It doesn't matter what the inclination is, it all comes to play. We did a summer camp last summer. I didn't want to do a summer camp. I was roped into it. I said, okay, I'm going to do this thing. What can I do that's easy? And we had 40 kids, and I said, okay, we're going to teach them 3D printing. And we showed them in 1 week. These are all reluctant kids who were sent by their parents, and they don't really want to spend a week at Cornell in the middle of summer. But they were there. So we said, okay, dream up your crazy project, and we're going to show you how to make it and print it on the spot and sell it online, all right? And they lit up. And you had kids suddenly making an iPod holder for a bicycle and selling it online in 1 week. Suddenly kids were asking questions like, what if somebody steals my design and prints the copy? And I've never heard a teenager ask IP questions from that direction, right? So suddenly you got them engaged in these things. This is a pencil holder, interesting pencil holder that one of these kids designed and made and is selling online in bronze. And there's lots of these. If you look at Shapeways, which was mentioned, There are 150,000 different objects people are selling online from $2 to hundreds, made out of all kinds of materials. It's a new kind, it's an industrial revolution at a scale that you can't even imagine. So how do we design for these things? So this is, everything we showed you here is about manufacturing, but how do we actually design things? And I like Brent's calling it Factory 2.0. I love that name, and I stole it, and I'm going to talk about CAD 2.0. We need a new kind of computer-aided design that will allow people to design things. So it reminds me of tea Earl Grey hot conundrum, and not in a way that you might expect. So Star Trek has the replicator that can make anything, right? And what do they usually make with it? Tea, right? So you have this machine that can make anything, and all you make with it is tea. And actually, sometimes they make a cheesecake, but it's usually pretty limited in what they do. So we have this problem, which we call in the lab the tea Earl Grey hot problem, and you bring a student to this machine that can make anything, and you tell them to design, and they usually will design a block with a couple of holes in it. It's difficult for people to take advantage of this huge open design space. It's like a blank page. So we need computers to help us design and explore new things. So traditional CAD doesn't cut it. It's too conservative in what it allows you to do. So where can we go from here? So I want to show you a quick couple of examples. One, so if you want to design a complicated shape like this, it's going to take you forever to describe it in CAD, forever to even think about it. You have to be a super duper expert to make something like that in CAD. So how do you do it? So there's a couple of new directions in CAD. Some of them, it's a reincarnation of all things. One is programming, so doing design by programming, not by working with geometry. So you can design something like this using a procedural language a lot easier than you can do by pointing and clicking. So there's a lot of work in that. In fact, the new file format that allows you to print things replacing STL is a kind of programming language. So it allows you to put in formulas that allow you to make complicated things like that very concisely using a program. You can describe a new material that is a kind of microstructure and then use that material to fill in things and so forth. So maybe it's going to be sketching. So for a while we worked on this software that will take a sketch, interpret it as a 3D object, and print it. Turns out that fewer people know how to sketch than to use CAD. So that's not going to go anywhere. So abandon that. Maybe we can do functional design. So I want to be able to say I have 3 bars, connect them in make a bracket that connects them in the optimal way. And it has to carry this load, and don't bother me with any more questions. Just call me when it's done, right? So this is how I work with my students. I want the software to work the same way. So maybe we can do that. So I'd like to start with some constraints and have it evolve or generate the design for me. So this is an example. This is running in real time of this kind of design optimization where you say, I'm harnessing structure. It's connected here. It's hanging off here. And give me the optimal shape, and here it's optimizing, and it's giving me a pretty good design. Now I can say, okay, actually I want a bar passing through the center, give me a design that leaves the space empty, and it's giving me a design. So these are new kind of AI algorithms. This is in 3D. This is not in real time, but you can have these kinds of functional design tools that find solutions for you based on high-level descriptions. We call them matter compilers, right? So it's a little bit like compilers. You say what you want, you hit enter, and it generates a design for you. Another thing has to do with materials. So we talk a lot about materials. How can we predict the material properties? And we said earlier that we can mix and match material. We can have 2 materials, 50-50%. Turns out that what the dot pattern of these 2 materials affects performance. If you have 2 materials, hard and soft, you make them 50% in a random pattern or in a checkerboard pattern, you get very different results. There's almost no theory to predict that. Material scientists are struggling with predicting properties of laminated composite materials, let alone checkerboard 3D random stuff. So we don't know how to do that, and probably the way to do that is going to be through modeling. This is an example of completely bizarre material. You can print materials that are auxetic. For example, you pull on them longitudinally, and they expand laterally. A very bizarre material, doesn't exist in nature. You can make it still with 50-50%. So the pattern matters, and we have no clue how to predict these things, and a new theory is needed. So we're working on a more data-driven, you make lots of these different things, you pull them, and you model them. And this is actually a product of a Keck National Academy project that was funded this a couple of years ago to make this project where you automatically generate models from data. And you can download Eureka with a Q, paste in your data, hit enter, and you get these interesting analytical models from it automatically. Another thing that a couple of my students are thinking of, and you see this more and more, are fab apps. These are applications that embody a lot of information about a design of a particular thing, and yet give you some freedom. So let's say you want to download and print a new toothbrush. You want to make your own toothbrush. The app, this is an app that would be dedicated to making toothbrushes. It has all the know-how about toothbrushes. It asks you a lot of questions, scan your mouth, scan your hand, whatever it needs to do, and it generates the perfect toothbrush for you, and it costs you 99 cents. You download it, you print one toothbrush, all right? So this is a kind of new business model that has to do with CAD that's dedicated for narrow markets, for one thing only, does one thing very, very well, and it's a way for manufacturers to get into the business. Last thing I want to show you in CAD is this sit back and relax kind of CAD process. This is a website that we've just created called endlessforms.com. And what it does there, you want to design something. Let's say you want to design a lamp, okay? But you don't know any CAD. You don't know how to do that. It shows you random things, and you say, I like this, I don't like that, and I don't like that. Based on your input, it creates a new set of objects and so forth. And just by saying what you like and you don't like, you create lots of things. And in about 1 month, we've had almost 2 million things generated here. There's a 3D print button, and you can print, and people have created these faces and spines and mushrooms and exclamation marks. I don't know what, all kinds of things on the fly with zero CAD training, all right? And people, just by this interaction, working in groups and so forth. So I think there are really fascinating ways to do that, and we want to integrate this with eye scanning now, so you can literally sit back and relax, just look, and based on where you're looking, the machine can design new things. So we want to take all these different modalities of CAD that go way beyond the traditional point-and-click drag kind of CAD and put them into a system where you can say what you want, give some specs, and it will design both the shape and the internal structure and all the multiple materials all at the same time to give you new designs. There's no way you can explore that manually. All right, last thing I want to say is that we are also on the verge of transitioning from analog to digital in manufacturing. The idea here is that you've seen a lot of technology move from analog to digital, from continuous to discrete. We're doing the same thing here. We're beginning to move from thinking of materials as continuous materials that are made of lots and lots of small pixels that are either there or not. So you can imagine the position process that puts material instead of a continuous process in a discrete process. And we see that right now this is a continuous circle, but it's really made of lots of pixels. So let's start thinking about objects as made of pixels in 3D. And depending on what kind of pixels you have, you'll be able to make lots of interesting things. And that will allow us to go from just printing with raw materials to printing with capacitors and transistors, and printing with CPUs, and printing with FPGAs and sensors and actuators and so forth. So the idea is to make a printer that basically rapidly assembles gazillion sand grain sized components into 3D together with all this raw material. And we've been working on different ways to do that, to pick up lots of things using adhesion. In this case, we have a print head. We wet some of it and dry some of it with light, and then it selectively picks up objects. And we can use it to make three-dimensional objects of various shapes and sizes out of raw components. And here's an example of a rook that's made out of 10,000 components. When you see this and you tell your grandchildren that you remember seeing that first object that was made out of 10,000 pixels, whereas in the future everything will be made out of gigavoxels. This is what it looks like, so nobody will believe you that it was that low resolution at some point. But eventually, we want to take these microcomponents as a powder and assemble them into these large structures that are composed of lots and lots of microcomponents. Somebody asked about microcomponents. These are 500 microns on the side, and they assemble into a 3D structure. So the next big phase, I think, of this thing that's coming after this revolution is moving from analog to digital. We saw it in computation, we saw it in communication, and now it's happening in manufacturing, and that's the next big thing. So you've seen this slide already, but we've talked about these 3 episodes. We talked about complexity is free, any shape goes. We're beginning to explore compositions of material. It's very, very difficult to anticipate what that's going to do. And now we're going to integrate functional behavior, electronics, photonics, all these different energy, all these different things. What is it going to do? It's a new design space, a new kind of materials. If there's one thing I want you to go home with, is to think about how is it going to affect your field, okay? And you have experts here who can give you all the input, but there is no field that this is not going to affect. So don't go home and thinking, oh, this is cool, but I'm going to do my own thing. No, you're going to have to think how it's going to affect your field, because it is. And the question is, are you going to be there or not? And I think that, human evolution has distinguished itself with the design, with new tools. And I think that this is the ultimate tool, and it's going to change everything forever. Thank you.
Hey, Hod, great job. Okay, we have time for a few questions, probably about 3. So, any questions?
Evgeny Gabrilovich, Yao Research. I'm particularly interested in the simplicity of input that you could achieve for such machines. You touched on this tangentially when you talked about kids, and then you talked about languages, which I'm afraid not everybody might be willing to learn. And then you talked about choosing out of multiple random designs. I think if this technology is to be adopted, it has to be super simple for everyone at home. So what do you envision to be the simplicity of input here? How do you allow everybody at home, whatever his specialty or expertise, profession be, to make use of those machines?
So it's an excellent question. That's the million-dollar question. Okay, how do we get people to use it? But it's happening. People are using it. It's a combination of having these machines accessible, and there's material inputs and things like that. But in terms of design, I think it's going to be a mixture of things. Some people will need a dedicated software for their particular thing. The people who make food and print cookies have asked me multiple times, is there a food CAD, okay, for making cookies? And it's not something that's going to work with fillets and holes. It's going to work with fillings and coatings and things like that. So I think we're going to see a proliferation of design tools for different areas. There's not going to be a one answer for everything. And how we do that is going to is the next big question. Yeah.
Sid Suryanarayanan, Colorado State University. First off, thank you for a very interesting presentation. As you start simplifying this CAD 2 or Factory 2, my concern is about quality control, because this is in manufacturing. So can you say something about it?
Right. So there's huge societal implication, and the question about quality control is a very important one. There's not just that. There's intellectual property, which was mentioned. There's quality assurance. There's liability. If you design a steering wheel, somebody puts it on, it breaks, who's liable? There's how do you make sure everything is the same? These are all issues that nobody has the answer to. And I think there's a lot of opportunity to test that. I think the importance of automated engineering tools that can verify these things in advance, that can predict properties, can have feedback while printing to ensure that the things being printed match the design. All of these things are going to be paramount. So I think these are big open questions. In a way, I think we have a better handle on the technological issues than we have on all these societal issues, and for better and for worse. It happens with the democratization of everything. you lose control. And usually it's for the better.
Yeah, my name is Haiying Wang. I'm from Texas A&M University. It's a very interesting talk. So the first question is on, you reviewed a very interesting roadmap for your AM process. So what's a timeline you were thinking about the episode 2 and episode 3 to happen, like the composite material and the future functionality? And then the second question is, as a material scientist, as a material engineer, I want to see what's the research need you will foresee for your, AM process.
Yeah.
What are the needs? Like I'm ceramic person and maybe some metallurgist over here. What's the niche research area you are foreseeing about?
All right. So timeline. And the research agenda. So timeline, I think it's so learning from the computer industry, and I think it's a similar, but it's just going to be a bit faster. So I would say, I'd say in 10 years, everybody will know what 3D printing is. Everybody, and I'd say you literally will have a hard time explaining to your grandchildren how you lived without a printer in your house. Right, literally. So I'd say in 40 years, everybody will have these things in their home, and so that's your timeline. In terms of the kind of material science challenges, I think they're all over, and there's you just pick whatever you like. You can go from kind of a very specific questions like how do you make titanium, crystals grow better and so forth, to questions that are more about automation. These are things that I like about. Forget about modeling any or improving any particular process. How can I automatically make a system that can watch what's going on and automatically improve it? Because there are so many materials and so many combinations that it is hopeless in my mind to try to model or understand any specific material, because there are just so many. There's a explosion of complexity. And the only way around it is to have data-driven processes that actually learn from what is printed and create models automatically. That's the approach we're pursuing, but I think material science will need to go in that direction of machine learning and AI to battle this complexity.
Okay, thank you.
All right, thank you.
Thank you very much. I'd like to ask the speakers to come up. We're going to go on and start the panel. So. First of all, thank you very much to the speakers. Outstanding. Very good stuff. So we thought we could just start out with, we pretty much have a good background on all the speakers, and you can see the diverse areas such as aerospace to medical to the future. Outstanding talks. But we wanted to kind of go into maybe some of the issues. We touched on a little bit of them, kind of like societal issues, intellectual property. But wanted to open up the floor to you to continue on with the questions that you didn't get a chance to ask and open up that dialogue. So.
Again, great talk, guys. I have a question for each of you, and in one line, if you were asked what is the great engineering challenge in 3D printing going forward for somebody to start a career, for like my kids or anybody, could each of you take a minute to say what do you think is the great engineering challenge in the next level for 3D printing? Thank you.
So I've got probably the most short-term answer out of this group here for that. And I really, again, there was a question about material science. We have what we're seeing with the four-dimensional energy input gradients that we have in these additive processes are really not the same types of energy inputs we're used to in traditional manufacturing, and that has guided the chemists and whatnot to formulate polymers in particular, or even metal alloys and whatnot. So I think there's still quite a bit of just in the weeds work that certainly you could fill a whole career with to really tailor materials towards additive manufacturing. The big polymer companies, Evonik and Arkema and Dow and whatnot, are just starting to look at that. But that's again, that's probably the most short-term response you'll get from this group. But there's a lot of work to be done there.
So you just heard me talk about this, but I think it depends if you're in academia or in industry. If you can afford to do long-term, I think one of the things that are most missing right now are design tools. We have fantastic. We have iPods with no music. Okay, We have machines that can play and make things, but we have nothing. We're still thinking about it the old way. So we need new design tools that can allow us to explore this vast new possibility. It's a bit longer term, but I think that's where the most impact could be had.
I would second that in medicine. I think one of the biggest challenges is figuring out how to use these technologies to do things that are not only kind of duplicates of, so say another way of making a metal implant instead of casting or machining is by additively creating it, and maybe you can make some interesting structures, but how to design that to fit a unique individual with their unique, their unique functional needs. And I think that's really where, you start getting really complex really fast. And I think that's where a lot of the systems today just fall apart. So I think there's a big need there to take advantage of the additive technologies and what they can bring, because today we're doing a lot of things that you could do, and some things you couldn't, but a lot of things you could do some other way, and it just happens to be better with additive. But I think in the future, there will be many, many more things that you can do with additive that you cannot do any other way. And those things really relate to very complex shapes and different types of porous structures and interactions of different materials within one part developed for one person.
And I think the beauty of these technologies at some level is just about anything you're interested in at the intersection of digital to physical realization. There's open questions out there, and so if it's design, if it's computation, if it's materials, there's still so much left to explore. And I think even on the business side, there's massive entrepreneurship opportunities all over the place. And one of the things, IP's been mentioned a bunch. Almost all of the initial patents for almost every one of the types of machines that exist are either just expired or are expiring in the next couple of years. And so there's huge opportunities for companies who could not play in the past because of, as Brett was talking about, people having all the legal battles. Those are going to go away, at least to a large degree, and already have started. That's how this whole huge explosion of these little extrusion machines, Fab at Home and others, have taken off in the last couple of years, because the original patents for these extrusion-based machines are gone, and so now it opens up the marketplace that nobody's worrying about getting sued on it.
Oh, they didn't care about the patents anyway.
And the hackers didn't care anyways, exactly.
Hi, John Oxendorf from MIT. Since my children are going to bring this into our home very soon, I'd like to ask about toxicity in terms of powder and fumes, and perhaps most importantly, cheese whiz.
Yeah, so this whole, like I said, all these impacts, the safety and liability are open questions. Nobody knows, and you would hope that Cheese Whiz is already safe to some extent, but there's I don't know if you're talking specifically about food printing, but that's definitely something that needs to be looked at. Let's put it that way. But when things are open source, and what we're beginning to see here is a movement towards open source hardware, which is that you download and make stuff. And just like there's security issues with open source software that people were worried about, well, turns out that security in open source software is as good as closed software. So my gut feeling is that open source hardware, if to draw the analogy, is going to be as safe for the same reason, if anything, just because lots of people do it and debug it a lot faster. So, but who knows?
Nick Feemster from Georgia Tech. Just had a question for the panel about reusability. So I could think of printing certain things or certain objects that I'd only want for a short period of time. For example, I go on a trip, I forget something, and then I want to, instead of throwing it away, maybe I want to make something new, the next time. Are people looking into sort of reusability of the raw materials and sort of ways to make that easier? And what's going on with that?
So you have the thermally processed materials are a lot easier to handle that with, the nylons, thermoplastics, things like that, be they amorphous or semi-crystalline. So there's kind of a clear path forward with that. Obviously, the processing temperatures get to be kind of tricky, especially with the polyaerols. You don't want that in your oven at home. But so with a lot of the low temp ABSs and things like that, you can, heat and cool and reuse those materials as well. That's kind of a big push within Boeing, is to move away from the thermoset composites it mirrors this in the additive manufacturing, and move into the thermoplastic composites, because again, that recyclability and processability and whatnot. Cheese Biz, though, I don't know.
Not sure if you want to read it.
I don't know if you want to recycle that one.
But I think the reusability is actually a major issue, particularly in Europe, that drives a lot of the research being done in these areas. And so the metals are easily recyclable. The polymers, yeah, you've got changes in molecular weight and other things that occur through multiple cycling, and you have a hard time with most of the currently available polymers getting them to be reusable at anywhere near their original properties. But it's the nice thing is that with these technologies is you're generating, with most of them, very little waste. You're only putting material where you want it. So in the first place, you're using less, and all the remaining material can be just dumped back in and reused again and again and again, with certain exceptions. But yeah.
There's the other side of it, though, which I want to mention. Anybody who has a printer like that in their office immediately sees a lot of waste being generated. At least in my lab, people, we used to have this thing in engineering: think twice, cut once. With a printer, you print many times, and then you start thinking. So this is exactly what's happening. People, you make the hole the kind of the right size. You print it. If it doesn't work, you make the hole a bit bigger. You print it again. It's still too small, and so forth. Instead of measuring. So I think, like printers, like regular printers, in the short term, it creates more garbage. At some point, people start thinking about recycling, and it's a little bit of economics. Companies don't want you to recycle, so it's the usual kind of thing. But in the long term, it's possible. With the digital manufacturing, when you actually make things out of components, it's fully recyclable. So the idea there is that you really print these things out of grains of microprocessors and sensors, actuators. You can take these apart like Lego and reconstitute it into something else. So you can take your fax machine apart and build it as a printer, and it's possible. And that's, I think, the ultimate form of recycling, but that's 50 years down the road.
Hi, sorry, a bit loud. Ollie Williams, Microsoft Research. So you made the analogy earlier about with sort of security and open source software, which is obviously a natural one. And the idea is that if I downloaded a piece of software on my computer, if that was a great piece of software, very well designed and engineered, we sort of rely on the fact that my CPU is going to execute it exactly like any other CPU would execute it and do exactly the same thing. So in the world where we all have our own 3D printer on our desk, and I download a brilliant design for an amazing thing, but my printer doesn't execute that manufacture perfectly, is there any work on, sort of decentralizing things like testing and ensuring that, especially if I've made a part from my car or something, that it's actually going to be good?
So we had one example. We partner with Lotus. They're now Lotus Renault GP, so Renault Formula One. They've been a long-standing research partner in additive manufacturing, and one of the projects about 5 years ago or so was to take one build file, send it to their machine, send it on our machine, build it, and pull all the mechanical coupons and have them all come out within a margin of error. And that took 4 months to get right. These are the more complicated processes, laser sintering and whatnot. Your laser has to be really tuned and things like that. But the process is in general a lot more complicated, and it takes a lot more attention than what we're used to. But it's certainly viable. We have we have a whole supply chain set up on that fact. But it's taken a lot of engineering from the from the near term, let's do it now type perspective.
And it took a long while for computers to get to the point where codes execute this exactly the same way. It didn't happen overnight. There's a lot of error correction going on behind the scenes to make that happen, and the same thing will need to happen with 3D printing.
I think an interesting thing about additive manufacturing from a quality standpoint is the ability to, in most of these processes, to look at each layer as it's being created. So if you think of a part that's traditionally cast or machined from a block that was created, some other way, you don't have the ability to look inside of it. Where here, you're actually seeing it be created. So if you have a good way to quality control each layer, and you have, the process parameters that go into the interlayer, variables, then you really can create more, even maybe more of an understanding of the quality of that part from the inside out than you can with traditional techniques, which I don't think has been fully exploited. But there's a lot of work I know on looking at layers and looking at, especially for metals, trying to make sure that you've got zero defects. And I think aerospace pushing that most, but medical interested there, as well.
Yeah, so this is Dan Zhao from Purdue University. So the printing has been used before to create today's integrated circuits. So the billions of transistors, there are a lot Then talking about this 3D printing, then how do you say, make a comparison? Then say the printing has been found having disadvantages, the number of issues with it. So how do you see the roadmap? So when you make a correlation with how printing is useful in creating today's integrated circuits, so have you thought about that? Okay, down the road, the future. So what's going to the roadmap? How far this technology can go?
It's difficult to say. I think everybody's looking at me. I don't know.
It's because you're talking.
I think it has to do with unleashing this complexity. So what happened with stereolithographic methods in microfabrication is that the complexity, cost of complexity came down. So you can make billions of transistors fairly easily, and that allowed you to make much more complex things at the same cost. This is what's happening now. So in the beginning, it's just about making conventional things more cheaply or differently. But what is beginning to happen, and this is the roadmap, you'll be able to make things that are a lot more complex than we can anticipate right now. And what will those things be? All bets are off. But that's where it's going.
I think what you're finding, if you look at the integrated circuits community, or if you look at the two-dimensional printing, even inkjet printing, limited to that we're talking not just millions or tens or hundreds of millions, but billions of dollars of R&D put into the development of those technologies. And right now, the entire marketplace for additive is only $1 billion. So we haven't put billions into R&D. But I was at a conference this summer where a lot of the major printing device companies are basically saying, we see this as the next wave. We've developed all this infrastructure and technology of making droplets to put them down. Now let's start stacking those droplets. And they were demonstrating in videos. They wouldn't give us very many details. They showed droplet printing of copper. So they've got working devices now that can print metal at the melting temperature of copper. And and there's other people working on how do we print high viscosity materials, polymer melts and things like that. So what I think you're going to find is as this grows, for the first time, you're now going to conferences, and not only are you bumping elbows with engineers, but there's investment bankers there asking you questions, and there's other people. And now we're at the cusp of, once a lot of money gets put into it, things can explode quickly because people see where the bottlenecks are, and none of them are technologically impossible. They're possibly difficult, but they're not impossible.
So Rahul Peshkar, MIT. So if I put energy, time, and the amount of raw material I take to make something on my left hand, and whatever it is I'm making on my right hand, and I say I do it by additive manufacturing versus subtractive manufacturing, it's clear from everything we've heard that for a highly customizable, flexible part or a low part count thing, additive manufacturing is going to win. What is not clear to me is that in many things that have high levels of symmetry, it's actually easier to make a very simple mold or something that makes that high symmetry part and then chop it away to make something customizable on top of that. Yep. So I think from everything I've heard that it should be a balance between additive and subtractive manufacturing, where you're actually using the best of both worlds in the same way like nature makes our own hands and then uses apoptosis to cut it away to make our fingers, so that the easy cases can be done that have high levels of symmetry cheaply with energy, time, and few amounts of raw materials. And then this is used to customize around that or do more complex things that can't be done in that very simple way. Would you like to comment on that?
Absolutely. I'd say you're correct because the hybrid additive plus subtractive is without a doubt, or even just traditional subtractive, is going to maintain a major part of the marketplace. There's no question about it. But to get back to, I think the question, I think you asked about volume back when Brett was speaking. Today, if you take some small complex, say small interconnects or something like that, using existing technology, existing machines, depending on the size, but you can make, in some cases, 120 to 200,000 little plastic widgets using additive more economically than injection molding. And so we're already seeing with pretty much just prototyping machines, they're not optimized at all for production, and they're not, and again, almost everything we've talked about, we're transforming energy at a point and moving that point discretely around. There are a tremendous amount of innovations that have looked at using lines of energy or transformation or transforming the entire area at a time. And then there's concepts for how do we transform material no matter where in a three-dimensional space. When we move beyond one point of transformation at a time, now it's going to become even, that's going to push that number higher and higher, even for simple objects in some cases. But yet, for now, without a doubt, simple parts, a hybrid approach, or even just simple subtractive approach is going to win out in most cases.
I would like to argue with you about this. I think that, to take the other point of view, that the thing you're not factoring in is that having a hybrid process is more expensive because you have to maintain two processes at the same time, and there's a cost to that. So it's a little bit like saying, you can make an analog circuit that's good for playing music, and you can have a computer that's good for calculation, and you want to have both. But in the end of the day, we use computers to do all of these things because it's just easier to have one kind of approach to do everything. And there's a cost benefit that factors in with this with the versatility.
Yeah, within Boeing, I mean, each one of our parts that we put on our aircraft gets traded against conventionally molded parts that have to be machined. I think the best example, though, maybe what you're talking about that I know of, that actually you can find instantiated already, is in the area of tooling. So tooling shops, the tool is their final product. That's what they're selling and whatnot. And there's a large number of companies that are doing a very good job of doing like they'll do a net-shaped casting, they'll machine that off, and then they'll put that into an additive manufacturing machine and then put the really, really fine details. They're not building up 50 pounds of steel and whatnot, but they will hybridize that to an extent. But it is true, though. I mean, you have to have the other thing you have to keep in mind with the other process is all the long-term costs. I wish I had a picture of it right now. We have a warehouse I think it's in Utah, that is literally 5 or 6 football acres in area. I'm sorry, football fields in area. It's literally acres in area, and it's all tool storage. So we have to, from an industrial perspective, especially aerospace, we have to think about the real long-term implications of those trades early on. And a lot of design engineers will get caught early. It's like, oh yeah, it's only $4 to injection mold that. That's great. They're not the ones that have to, keep those tools maintained for 50 odd plus years. So there are it's a very complicated situation. But there is some hybridizing already.
This is RC from Eastman Chemical Company. I have a couple of questions. The first one is, what is the landscape of additive manufacturing and how are developing countries picking on that? And next is, one of the killer apps could be in hobbies or in pleasure activities. In that case, like how the photography is there, how can we follow the development in this area? Is there anything like a magazine or blogs where we could, read for the, amateur for 3D printers, something like that? Thanks.
Well, there's a huge industry around this Maker magazine, and there's a huge industry around these hobby 3D printing, but I'm not sure if there's a magazine yet. You have a great idea there. So go for it. Faber.
Yeah, Maker, I think, has one. I think so.
For 3D printing?
For that spectrum, beyond 3D printing. So.
And I think I've thought quite a bit about the developing world and how this impacts that. And I think there are very clear and compelling ways that this removes some of that angst between, we're sending all of our labor and our manufacturing to the developing world, because this allows a lot of that to come back from the developing world, but at the same time without taking anything from them, because they can also use that there as well. And I think it's a great equalizer at some level, because the infrastructure needed to do additive manufacturing is quite small. It's sort of like the developing world is not putting in landline telephones to now get up to, it's all wireless, right? Because the new technology, cell phones, is far better, for a developing world infrastructure. I think in the same way, we're not going to see the developing world going in and putting in massive, at least in up and coming developing places, not putting in massive facilities and foundries and forging facilities. They're going to say, that's too much infrastructure. We're going to jump straight to things we can use the natural resources here and print them out and organize them. So I think it's a major issue.
Yeah, you could see the same thing already happening with Fab Labs. So it's a good example, which is kind of Fab Labs from coming out of MIT. Neil Gershenfeld are these hacker spaces where people make and build things. And when these are put in rural areas, let's say in Africa, what happens is that people make things they need. They have ideas, they know how to make it, they make it. They don't have to rely on some big US companies to think that there's a market. They just go and make what they need. So there's huge, on one hand, the ability to make things and close the loop a lot closer. But the bigger impact, I think there is huge empowerment that follows from that. So we put open source 3D printers in South Africa, and kids suddenly want to, they make things, and then they come and say, okay, where do I study about this? Suddenly there's a need. It can make something, and then follows the thirst for education and for innovation and entrepreneurship. So I think it's a big equalizer, like you say, and it's going to have huge impacts.
Hi, Scott Chell, UC Santa Barbara. So I'm wondering if there are particular challenges associated with using these techniques to generate materials with not only precise structural and mechanical functionality, but with chemical functionality. And in particular, I'm thinking of applications in biology and medicine, where you may want to generate materials that have particular recognition factors, growth factors, or enzymes, which are very sensitive molecules in terms of being subjected to shear and temperature. And so I'm wondering what kinds of constraints does that generate on these development of these processes, and are there efforts to try and improve them?
I can give two examples of that, and I don't want to. One is people are using are printing in custom medications. The idea is that you print a pill and it has different ingredients at the right spatial configuration, so they dissolve at the right time and the right combination. That's an example where the shape doesn't matter, but it's the chemical composition that actually matters, and it's tailored. So it's personalized medication, if you like. And so that's one example where we're controlling this kind of thing. And then there are other processes that have to do with color. And in another example, in bioprinting, people put different cell types in different locations in order to create models of a three-dimensional cell culture. So going from a 2D petri dish to a 3D cell, a heterogeneous tissue cell culture for modeling the behavior of a, so you can do tests in a kind of 3D petri dish. So that's an example, again, where you want to control the chemical gradients in very precise ways to emulate in vitro biology. So that's these are two examples. So I'm glad you brought that up. It's a great example how you take this capability and move away from geometry and think about other kinds of things you can print and use that.
It's a big area. I mean, I'll be in Portugal at a conference next week, and a lot of the stuff there is on medical things where people look at printing different kinds of tissue, different multiple material, the scaffolding, and then in some cases, like you're saying, putting certain shear and strain histories into them as they're building them, because you get a different response from living tissue under those scenarios, and chemical gradients as well as thermal and stress and strain gradients. And what this is doing is it's making people who work in the area of sort of synthetic biology and other things, you get three-dimensional responses that are very different than petri dish responses. And people are saying, hey, we've come so far with petri dish type things, but to go to the next level, we've got to mimic the full three-dimensional stress strain chemistry. And yeah, a lot of people are looking at it. It's got a lot of NIH money right now in different aspects of that going on.
Because historically, those two things have been separate. The form has been separate from the biology piece of it. So you'll make the form, and then you'll seed it with the biology because of the, the factors of things needing heat or pressure or whatever to actually get extruded. So I think more and more you've got to see those come together, and that has to be a key part of being able to build something like an organ, that can function out of the machines, being able to do it real time, in a layer that's sealed off from other layers, do things that you can't necessarily get in and seed later. So I think it's a key area.
Hi, I'm Michelle Povinelli from University of Southern California. Hod, you talked about the maker movement, and I think the maker movement is a very optimistic movement, and that it's trying to give people tools to make things. But realistically, there are a lot of people who don't want to make stuff at all. And I think the best example of this is cooking. Probably even a lot of us here don't want to make food, which is why we have Trader Joe's and food courts at malls. So I wonder if, psychologically speaking, apart from the hobbyists, if the biggest application of these technologies would be something like a food court, where there will always be people who do small-scale manufacturing of custom products, and you might go to a mall and have a bunch of people making a bunch of custom things using these sort of techniques, but then who cater to people who want to buy things, which unfortunately is all of us.
That's very much a possibility. We've had numerous discussions of this type in the lab. How this technology will play out, and we really don't know. There's probably going to be all the way from a printer at home to Kinko's. You buy books on Amazon that are pre-printed. You go to Kinko's to print 1,000. You print at home something if you want you want a few copies. There's the whole variety. There's probably going to be all of these. Definitely there are people who would like to be able to download recipes and print them, and it is more automatic than making it yourself, actually. So it is convenient, and that's kind of my perspective as well. But if you're into making sophisticated pastries, but you don't have a steady hand, you can. That's a way to do that, and maybe people who can't do it right now would be interested if they only had those tools. So I think it's just a huge space, and we'll see how it plays out.
Chris Badger, Carnegie Mellon. So I want to talk about maybe the legal implications about failure of these devices, right? So let's say I'm interested in bicycle pedals, and I buy one from Shimano, and I'm riding my bicycle, and this pedal fails for some critical defect. And I can say, okay, so Shimano sold me this, so they can kind of go back. And it's kind of a centralized kind of responsibility, right? But now we have a case with AM where you have, a user involved with the material, involved with the maker bot, for example, right? So you have all these multiple parties all linked up, right? So let's say that same example happens, and my bicycle pedal fails, and my son crashes into a car or something terrible like that. So then how do you parse out who's responsible for this, right? Is it maybe there's a good design that I download, the design is perfect, but then the 3D printer is just slightly flawed, and then that leads to problems, or maybe the raw materials are out of spec, right? So how does that kind of play out?
I think nobody knows. It's literally playing out. It's a big problem, and nobody knows what to do with this. I don't know if there's anybody here in the legal profession, but that's definitely something you can make a career out of thinking about this.
Like that question. Yeah.
Go ahead first.
I was going to say, for the medical industry, I think that question will keep things centralized. It's one of the big keys is that nobody wants to take that risk. I mean, you can take that risk for certain things, but for things that are really critical, you don't want to take that risk. And it's the reason why these companies put millions and billions of dollars into research and testing and all that to make sure that product's safe. And at home, even if the design was right, there are so many. I mean, if everybody had 10% of the liability there, everybody's going to disclaim everybody else, so nobody's going to have any liability. And I think that may work for some industries, but I think the medical industry, that's a tough one.
So what happens today if you download software and that software causes a problem? I think it's not unlike what's happening with, so you download, and it's running on your computer, and so there's a mixed liability there. Mm-hmm. So although it sounds very complicated, I think it's not totally foreign. These things are happening with the internet all the time, and somehow it works out.
But I think, from production at Boeing and GE and medical, that, like you said, centralized, repeat, and you have to have traceability back to the beginning. And so those are issues that are relatively straightforward. I think your question is like, what happens if Shapeways, somebody designs a bicycle pedal and they advertise it on Shapeways? I think what's going to happen is Shapeways is going to say, these things are not fit for any use. They're just for, for looking at, and try to hand off their liability. And if a designer represents otherwise, we're not representing that that's the case. That's going to cause big trouble for Shapeways, iMaterialize, and other. Yeah. But I think at some level they will end up, passing off some of that, or they'll get sued and go under, and somebody else will come up with a way to actually pass it off. But Google has to handle with that sort of stuff all the time, right? Like, Fourth Amendment stuff is all over the place, and so.
Well, if software, banking, there's plenty of damage that software can do to you. Yeah, it's these things. A lot of these things have already been addressed. But
and for anyone who thinks that the quality control is straightforward and trivial, I'd love to invite you to a qualification meeting. It's for an additive manufacturing company. It takes a lot of investment to ensure that we have the.
One of the key points of the question, though, is as you get into distributed manufacturing, you get into distributed lawsuits. And that's going to be a big business in the future for some lawyers. Yeah. But you typically don't do lawsuits unless you think you can win something out of it. And so if you're suing a 12-year-old at home that printed a plastic part and someone got hurt from it, can you get money out of that? It's a big question.
So it doesn't seem to stop the recording industry. So
that's true.
I think it's only now becoming an issue too. As you look at Shapeways or iMaterialize, and you look at Shapeways. I know you look at most of it. You get a lot of jewelry and a lot of things that aren't functionally all that interesting. So I think only now, as people are getting more easy tools to design something to fit their particular bike or their particular stroller or whatever it is, you're going to find more of this stuff. So I don't know that we've seen actually much of it.
There is legislation on safe haven for aggregators that merely communicate designs but aren't responsible for them. So I think it's going to evolve.
But there are people already who are designing, replacement parts for blenders in their kitchen that are breaking on Shapeways and things like that. Now you've got issues of flying parts, and you've got issues of contaminating food, and there's no warnings on anything when you go to buy that. So it's a major issue. And I think you're going to see a lot of lawsuits setting precedents in companies. It's going to be really fluid for the next 10 years, would be my guess.
There's also copyright issues too, right? If you take a Mickey Mouse and cut his head off and put your new intellectual property, or are you infringing upon that? And so it's another big area.
Lonnie Love from Oak Ridge National Lab. Last year, Hod, I had a similar experience. My wife roped me into helping First Robotics. It was a nightmare, but the school did not have a shop, but they had a 3D printer. And the first night, we sat down and taught the kids CAD, and it really unleashed their creativity. How can we get this technology in every school? Because kids need to be building things, and right. And it really is an interesting opportunity.
Right. Well, I can't be more enthusiastic about what this is going to do to education and unleashing creativity and empowering kids to realize they can design things. It's not about making teaching models. It's about letting the kids make things. I wrote a OSTP report about what the government needs to do with 3D printing. I wanted the government to stay out of it, but I can't actually say that. I couldn't say that. So the only thing I could really say is put a 3D printer in every classroom. This is what we really need. Most adults, let alone kids, have not seen anything being made in their own eyes. And I think there's huge empowerment in engineering and seeing that happen. So I'm all for it.
And you could really pick out the kids that were going to be the engineers, because they would sit there and watch it.
Exactly.
They would just be enamored.
They would even move their head as it's printing. Yeah.
But there's already, I think, close to 10,000 in educational environments right now. So it's exploded in the last few years. I think that's my recollection. The number I heard this summer was 10,000 additive manufacturers.
But just like there's a computer in every classroom, there has to be.
There will be. Yeah, but it's propagating much more quickly than computers did into classrooms, without a doubt. I bet we're way ahead of the curve of propagating into education. Doesn't mean we should sit on our laurels and think it's going to complete. It still needs some work. But
there are programs like Society of Manufacturing Engineers, Bright Minds, that really speak to, I think, the passion of everyone who's involved in the industry. Yeah. And then there are some regular efforts.
Well, the challenge has been, so we've done quite a bit of work in education. It's not, the excitement is there. The challenge is to get it into the standard curriculum, okay? Because it's packed. So the question is, how can you teach square root with a 3D printer better than without it? And that's, right now, that's at the point we need control, experiments, data to showing that having this in the classroom accelerates learning. And that's hard data to get, but that's the next step. The enthusiasm is there, that's not the problem. The lowest cost ones are about $1,000.
Luca Carloni, Columbia University. So for all of you, maybe more for Hod, one image that keeps coming up is the idea of somebody printing something in his own home, in his own garage. No? And so I can see that aspect and maybe the need for tools to help people print what they want. But in terms of more like collaborative engineering or collaborative geographic distributed engineering and the potential for, if you will, regenerate and the enthusiasm for engineering with, like, for instance, also with respect to computer engineering, but not just that. So can you comment on that and what additive manufacturing can bring and what are the challenges to it?
Yeah, well, that's a great point. You know, I see all these hacker spaces happening, the maker movement, and what people tell me is that it's not the tools that bring the people, it's the other people that bring people into these places. It's a place for quote-unquote nerds to hang out with like people, and they build things, and it's really the social element of making that really makes that take off. So I think you're absolutely right. There's the collaborative element that is also part of this bigger picture of what these manufacturing tools, what manufacturing at home makes and means, and what manufacturing in these collaborative spaces means. And it's very empowering that way as well. It allows people to share ideas a lot more easily. You can ship ideas. You can work on a physical thing at different sides of the planet at the same time. So it gives a new meaning to collaboration. And it also allows people to work together in the same spot in much more connected way than otherwise. So this is a great point.
And it's happening in a lot of multinational companies where they will actually do physical production or prototyping in all their various facilities and collaborate that way. A lot of people in this industry talk about it like if a picture is worth 1,000 words, then how much is a part is worth, and everybody throws out their own number. But it's the idea. Yeah.
Million words.
Million words.
Hello, Bob Barsati, Arkema. I had a question about what the resolution, like the state-of-the-art resolution for different materials are in terms of pixel size, and how that'll become more important as people try to put functionality at exactly the right spot in a device or have a gradient for a medical application, things like that. And are people trying to push that lower and lower, to get more specificity and precision?
Yeah, I spent quite a bit of time working on minimum resolution, feature size resolution, and laser sintering, and there are technical details with each process that are different and whatnot. But in general, the first thing you look at is your layer thickness. Is the first thing, and then after that, you can get into energy input minimum dimensions. So you're typically on the order of 100 micron, 80 micron, 50 micron, and whatnot. Depends on the process and the materials, and then the spot sizes are also very challenging as well. So CO2 lasers are have 500 micron spots with a gradient and whatnot. That gives you the order of magnitude that we're at right now. Typically, you can build walls, down to, if you're really, really careful, 3/4 of a millimeter, half millimeter, functionally in robust materials. You can make really fine things that are, that are just as good. Might as well not be there, basically. But that's functionally where we're at in terms of industry right now.
Well, a lot of it's driven by need. So I often, I ask companies, can you make it higher resolution? And they say, yes, but why? What's the killer app that needs higher resolution? So I think it's possible to bring it lower, but the question is why, and is that the best place in terms of opportunity?
Yeah, and like you said, I think most like manufacturing production ready type machines are in the 100 microns to 200-300 microns for some of the worst ones. But you got jewelry prototyping or wax production machines that are around 10 micron or below resolution. So it really, all of these can be, has a changeable resolution. The tighter the resolution, the slower the process is going to go. So it's really a trade-off in most cases.
You said you were from Arkema, though, is that right? Yeah, so well, first question is, I'll throw it right back at you. How fine do you want to grind the powder? Cause we'll
Yeah. So, well, different. One of the things you can do also is you can have in the center of the structure you can have very coarse resolution, and only near the edge you need the high resolution. So you can be a lot smarter. Right now we have uniform resolution, which is kind of not necessarily optimal.
Well, let me make one exception to that, which is the electron beam process by Arcam now. When they're doing a fill, they're using the higher power, low resolution. But when they're doing the outside contours, they split into 50 melt pools that are running simultaneously by moving the electron beam around so quickly that we have 50 small melt pools doing the contouring. And so that's an example of, well, electron beam is much more dynamic of an energy source than a laser because you don't have mirrors to move. So you can move it so quickly that you can, it acts as if you have 50. So, yeah, but that's so it's coming, but I think we need to move on to. It looks like
you do see people judging, taking and trying to decide whether you should go lower, layer thicknesses or higher layer. I mean, there's some of the processes actually moving up, trying to move up because they find more value from being faster than they do from getting more resolution. And then you're finding, variable layer thicknesses as well as variable spot sizes within a layer. So I think there's a lot of that kind of going on at once, but it isn't all moving. It isn't all moving down. Some of them are definitely started really low and had great resolution, but feel like they'd rather have speed versus resolution and give up some of that and move faster.
Okay, I think that's going to have to do it at this point. Well, one more question. We'll get one more in.
My name is Whitney Kallela. I'm from Pacific Northwest National Labs. Thank you for some excellent talks. I really appreciate the quality of your talks. I just had a curiosity question. I was just trying to understand where the technology is in terms of cartilage replacement. It looked like you gave an example of replicating a person's cartilage and then injecting it in place. It seemed like that could be a potential growth market.
There's a whole area there's a whole field of emerging field called bioprinting, which has to do with printing live tissue, and I'd say it's within reach, but there's a lot of animal testing and that needs to be done to actually demonstrate that. So it's in the lab it's being done, but it's not yet proven.
I would say even some of the simplest structures like bone you could think of as being fairly simple in places that don't need load, so think of replacing a part of the skull or some area that's not exerting a lot of force. It's still not there. We don't see commercial applications of those things yet, and cartilage is tough, because one, it's immediately under load and function. I mean, it's got to be, it needs to be exactly as it should be, or it's going to get torn up, chewed up really quickly. So I think those things are still some ways off.
Okay, well, thank you very much. We really appreciate it.
Thank you.